In today's lesson, we're going to do an introduction to probability. Welcome back to my channel, Numerics with Nadia, and let's get into our lesson objective for today. By the end of this lesson, students will be able to understand and calculate the probability of compound events, including independent and dependent events. Now, what comes to mind when we think of probability? For example, let's think of flipping a coin. What do you think the chances are of flipping a coin facing heads? Or what do you think about flipping two heads in a row? Stuff like this is probability, and we'll get into some definitions just so we know what to expect for the lesson plan. So the first word is probability. The probability of something is a measure of how likely an event is to occur. Then we have an outcome. An outcome is a possible result of an experiment. Then we have the term event. An event is a set of one or more outcomes. Next, we have a compound event. A compound event is an event made up of two or more simple events. An independent event are events where the outcome of one does not affect the other. Next, we have dependent events. Dependent events are events where the outcome of one does affect the other. And last but not least, we have mutually exclusive events. We won't get into that this lesson, but I'll do another lesson on that next time. Mutually exclusive events are events that cannot happen at the same time. Once you guys have these definitions written in your notebook, we will look at the probability of compound events. Now we're going to be analyzing the difference between independent events and dependent events. For independent events, the outcome of one event does not affect the outcome of the other. And now we'll compare this to the definition of a dependent event. So dependent events, the outcome of one event does affect the outcome of the other. So independent events, the outcomes don't affect each other, but dependent events, the outcomes do. They do depend on each other. So this is important because once we look at the formula, we'll be able to see the differences here. They might look similar, but there is one key difference, which you guys will see in a moment here. Let's first look at the formula for independent compound events. The formula reads the probability of A and B would be the probability of A times the probability of B. So for independent events, that's the formula, as simple as that. Now we'll look at the formula for dependent events. For dependent events, the probability of A and B is the probability of A times the probability of B given A. So that's what the B bar A stands for. That is the probability of B given A. And why is that? That's because the probability of B depends on the probability of A. So we have to take that into account for dependent events. We'll see how this works once we do a few examples, but go ahead and write these formulas in your notebook. And now we'll get into a few examples. For example 1, it's just conditional probability, and our scenario says a standard deck of 52 playing cards is shuffled. One card is drawn at random. Let event A equal drawing a red card and event B equal drawing a heart. Find the probability of A, probability of B, and the probability of B given A. So to start off, let's go through the things that we know about a deck of cards. We know that there are a total of 52 cards in a deck. We know that the number of red cards would just be 26. Half of the deck is red. And then we know that there are 13 hearts in the deck, right? Each suit has 13 cards. So those are our known variables on the right here. And now we're going to start looking at what we wanted to find. So finding the probability of A would be the probability of drawing a red card. And we know that there are 26 red cards out of a total of 52 cards in the deck. So it would be 26 over 52, which when we simplify gives us 1/2. Now we'll do the probability of B, which is the probability of drawing a heart. We know that there are 13 hearts in the deck, right? Every suit has 13 cards. So we would just say 13 over 52. 13 hearts out of the total 52 cards in the deck. And when we simplify that, that is 1/4. Lastly, let's do the probability of B given A. Now, what does this mean in this scenario? The probability of B given A would be the probability of drawing a heart given that we already know that the card is red. So we know that there are 13 hearts in a deck of cards, and we know that there are 26 red hearts. So our fraction here would be 13 over 26, which would simplify to 1/2. So that is example 1. Now we'll get into example 2. Example 2 is independent compound events, and we are being asked, what is the probability of flipping heads on a coin and rolling a 4 on a number cube? So here we're going to write out our formula. The probability of A and B is the probability of A times the probability of B. That is our formula because this is just independent compound events. Now, the probability of A would be the probability of flipping heads on a coin, and the probability of B is the probability of rolling a 4 on a number cube. So we know that the probability of A is 1 over 2, right? There are two sides of a coin. One of them is heads, so the probability would be 1 over 2 for flipping heads. And the probability of rolling a 4 on a number cube is 1 over 6. There are 6 sides on the number cube, so it would be 1 over 6. So the probability of A and B would be 1/2 times 1/6, which gives us 1/12. And that is our answer for number 2. And now we'll get into our third and final example for today. This will be a dependent compound event, and it is asking us, what is the probability of drawing 2 aces from a deck of cards without replacement? So here we have probability of A, which is the probability of drawing an ace. We know that there are 52 cards in a deck, and 4 of them are aces, so the probability of A would be 4 over 52. And now we're looking for the probability of B given A. So given that we already pulled an ace, what is the probability of pulling another ace? Well, we started off with 52 cards in the deck, but we already pulled one. So that means that there's 51 cards left. And if we already pulled one of the 4 aces, that would mean the probability of getting an ace given that the first was an ace would just be 3 over 51. So the probability of A and B here would be 4 over 52 times 3 over 51. And when we do that, we end up getting 12 over 2,652. And I know that's a little bit hard to envision. So as a percent, that is 0.45%. So very, very unlikely, but that would be very lucky as well. That wraps up our third example for today and our lesson for today. I hope you guys enjoyed this video. Please feel free to like it if you enjoyed it. Comment any questions or any other video topics you would like to see down below. Subscribe if you haven't already. Share this video with a friend, and I will see you guys next time.